Hello guys, welcome to this learning session with Was Moses, your mathematics teacher. We'll be looking at advanced level GCE on a topic vectors. We'll begin by looking at some few key points. First, let U cap be a unit vector in the direction of a vector U. Then U cap will be equal to the vector U over the magnitude of the vector U. Next, if vector A equals A1I plus A2J plus A3K is the position vector of a point on a line, and the vector D equals D1I plus D2J plus D3K, a vector in the direction of that line, then the vector equation of the line L will be given by R equals vector A plus lambda vector D, where lambda is a parameter. Secondly, the Cartesian equation of the line L will be given by x minus A1 over D1, which is equal to y minus A2 over D2 equals z minus A3 over D3. Please, here care should be taken that A1, A2, and A3 are coming from the position vector of a point on that line. D1, D2, D3 are coming from the vector in the direction of that line. Next point, if vector P equals P1I plus P2J plus P3K is the position vector of a point in a plane, and vector N equals AI plus BJ plus CK, a normal vector to that plane, then the vector equation of the plane in scalar product form will be given by R dot N equals V. Next, so secondly, the Cartesian equation of the plane will be given by AX plus BY plus CZ equals V. And in any of these cases, D is a quantity obtained by taking the dot product of the vector P and N. Next, the perpendicular distance D from a point whose coordinates are x1, y1, z1 to a plane with equation AX plus BY plus CZ equals D is given by D equals AX1 plus BY1 plus CZ1 minus D all over the square root of A squared plus B squared plus C squared. You will notice here also that the X, Y, and Z in the equation of the plane are replaced by the coordinates of this point, and the coefficients of X, Y, and Z are what is used in the denominator as a magnitude. And the D in the equation of the plane is sent to the other side where the components of X, Y, and Z are represented. Next, given any two vectors A and vector B in a plane, a vector N perpendicular to both A and B is defined by vector N equals vector A cross vector B. That is the cross product of the vectors A and B. Next point. Let theta be the angle between two vectors A and B such that the magnitude of vector A is equal to A and the magnitude of vector B is equal to B. Then the magnitude of vector A plus B will be equal to the square root of mac A squared plus the magnitude of B squared plus 2 times the magnitude of A times the magnitude of B times the cosine of theta. This formula is also equivalent to the square root of the magnitude of A squared plus the magnitude of vector B squared plus 2 times the dot product of A and B. Next, the magnitude of vector A minus vector B will be equal to the square root of the magnitude of vector A squared plus the magnitude of vector B squared minus 2 times the magnitude of vector A times the magnitude of vector B times the cosine of the angle theta, which is equivalent to the square root of vector A magnitude squared plus the magnitude of B squared minus 2 times the dot product of the vector A and B. Next, if we are given the two lines with equations as shown, R1 is equal to A1 plus lambda D1. R2 is equal to A2 plus mu D2. Intersect. If we are told that these two lines whose equations are the R1 and R2 intersect, then at the point of intersection, R1 is equal to R2. So which means that in a case like this, you just equate the two equations together. Now, if you have the two lines and we are told that theta is the acute angle between the two lines, then we need to identify the vectors in the directions of each of these lines, D1 and D2. And once that is done, the dot product of those two vectors, D1 and D2, will be equal to the magnitude of D1 times the magnitude of D2 cos the angle theta times the cosine of the angle theta. Or to find the cosine of the angle theta, you find the dot product of the vectors D1 and D2 over the magnitude of D1 times the magnitude of D2. We are going to be looking at these application exercises to actually review or practice what we have learned on the key points and what we also know in vectors. The first application exercise is taken from PATH GCE 2015 paper 1 question 14. It reads, the vectors A and B are such that the magnitude of vector A is equal to 3, the magnitude of vector B is equal to 5. And the dot product of the vectors A and B is negative 14. Find the magnitude of A minus B. Solution. To find the magnitude of A minus B, we know that the formula is given by the magnitude of A squared plus the magnitude of B squared minus 2 times the dot product of A and B. So substituting, we have 3 squared plus 5 squared minus 2 times negative 14 as was given in the question. So you take the square root. Simplifying this result gives 9 plus 25 plus 28, which further reduces to the square root of 62. And since 62 is not a perfect square, we leave the answer like that. Next application question, which is question 2, still taken from past GCE question. I read, the angle between vectors, the angle between two vectors, A and B is 60 degrees. These are the vectors A and B. Given that vector A is equal to 3 and vector B is equal to 4, find A, the magnitude of the vector 2A plus 3B. B, the magnitude of the vector 2A minus 3B. Solution. Mark A is equal to 3, Mark B is equal to 4, and theta is equal to 60. This is just the information we have in the question. Now, A, we use the formula we know to find the magnitude of 2A plus 3B, given by the square root of the magnitude of 2A all squared plus the magnitude of 3B all squared plus 2 times the magnitude of 2A times the magnitude of 3B times the cosine of the angle theta. And given that the magnitude of A is equal to 3, the magnitude of 2A will be 2 times 3, which is 6, and 6 squared gives 36. Similarly, the magnitude of B is 4, meaning that the magnitude of 3B will be 3 times 4, which is 12, and 12 squared is 144. 2 times Mark 2A is 2 times 6 times Mark 3B means times 12, which is still 144. And since theta is 60, cos 60 is a half. This reduces to the square root of 252. And as is said, the final answer in basic form is 6 root 7. B, the magnitude of 2A minus 3B is obtained from the formula Mark 2A squared plus Mark 3B squared minus 2 times the magnitude of 2A times the magnitude of 3B times the cosine of the angle theta, all that square root. Again, as we have already seen, this 2 reduces to 36 plus 144 minus 144 into a half, which further gives us the square root of 180. And the square root of 180 in set form reduces to 6 root 3. We move to the third application exercise, which is still taken from Path GCE 2017. Paper 2, question 8, Roman numeral 2. It reads, the equations of two lines L1 and L2 are given by L1 is such that R is equal to 13I plus 4J plus 11K plus lambda into 3I minus 8J minus 6K. L2 is such that R is equal to 5I plus 22J plus 7K plus mu into 7I minus 17J minus 5K. Find A, the position vector of the point of intersection of L1 and L2. B, the cosine of the acute angle between L1 and L2. Solution. A says we should find the points of intersection, but we know that at point of intersection, the two lines are equal. The two lines have the same equation, or the equations of the two lines are equal at point of intersection. This implies that the equation of the first line, 13I plus 4J plus 11K plus lambda into 3I minus 8J minus 6K must be equal to 5I plus 22J plus 3 plus 9K plus mu into 7I minus 17J minus 5K. Now, to find the point of intersection after equating these two equations, we need the values of lambda and mu, so that substituting in any of the equation of the lines will give us the position vector of the point of intersection. So we form three simultaneous equations using the components of I, J, and K in these both equations. For the components of I, we have 13I or 13 plus 3 lambda for the components of I in the first equation equals 5 plus 7 mu. This simplifies to 7 mu minus 3 lambda equals 8. We call that equation 1. For the components of J, in the first equation, we have 4 minus 8 lambda equals, in the second equation, we have 22 minus 17 mu, as you can see on the slide. This simplifies to 17 mu minus 8 lambda equals 18. We label this equation 2. Also, for the components of K, in equation 1, we have, the first equation, we have 11K, which is 11 plus negative 6 lambda. So which is 11 minus 6 lambda for the first equation, and 9 minus 5 mu in the equation of the second line. So giving us 11 minus 6 lambda equals 9 minus 5 mu, which reduces to, or which simplifies to 5 lambda, or 5 mu minus 6 lambda equals negative 2. And we label this equation 3. So please, at this level, you will remark that if the equation, or if in the question you were asked to show that the two lines meet, this is the same approach you will follow. But when, after forming these three equations, you choose two of them, as we are still going to do, solve for the values of lambda and mu. And when that is done, the equation you did not use should be used to test the values of lambda and mu. And if the values of lambda and mu satisfy that third equation, the equation you did not use in finding mu and lambda, then you conclude that the two lines intersect. But in this our case, we are not showing because we are already told that they intersect. So what we need is just to find the point of intersection. Here we choose two equations, find the values of mu and lambda, solving them simultaneously, and substitute one of the values in one corresponding equation. So here I have chosen equation 1 and equation 3 and solved it simultaneously to obtain mu equals 2 and lambda equals 2. But you can still pause the video and you take a piece of paper, do the solving to actually be sure of the values of lambda and mu. With this value of lambda and mu, lambda equal to and mu equal to. Now, looking back at the two equations of the lines, to find the position vector of the point of intersection, we simply just choose one of the equations. And here I have decided to choose the first equation. So R will be equal to 13I plus 4J plus 11K. Lambda now is replaced by 2 into 3I minus 8J minus 6K. This simplifies to 19I minus 12J minus K. B, we're asked to find the cosine of the accurate angle between L1 and L2. We let theta be that angle between the two lines. Now, looking back at the equations of the two lines, we know that to find that angle, we need to identify the vectors in the direction of both lines. And in the first line, the vector in the direction of that line G1 is 3I minus 8J minus 6K, as you can see represented here. In the second line, the second direction or vector in the direction of the second line is 7I minus 17J minus 5K, as you can see illustrated here. So those are the direction vectors. Now, with those direction vectors, To find the cosine of the angle, this is the formula. Cos theta is equal to d1 dot d2 all over the magnitude of d1 times the magnitude of d2. Replacing these vectors d1 and d2 and simplifying these ratios, we have d1, which is 3i minus 8j minus 6k, dot d2, which is 7i minus 17j minus 5k, all over the magnitude of d1 is 3 squared plus negative 8 squared plus negative 6 squared times the square root of d2, which is 7 squared plus negative 17 squared plus negative 5 squared. Now, the dot product of this means we multiply the various components. The I components, we multiply them, multiply the J components, multiply the K components, as we can see here. 3 times 7, 21, plus negative 8 times negative 17, 136, plus negative 6 times negative 5, 30. All over, simplifying 3 squared plus negative 8 squared plus negative 6 squared gives 9 plus 64 plus 36 times. Similarly, here we have 49 plus 289 plus 25. This reduces, or this simplifies further to 187 over the square root of 109 times the square root of 363. To further reduce this, we know that 39,563 is divisible by 121. And the square root of 121 is 11. And that 11 can divide 187 to give 17. That is why we have 17 over the root of 327. Thus, we are saying that the cosine of the angle between the two lines is the quantity 17 over the root of 327. We move to the fourth application exercise, which is also taken from PATH GCE 2016, paper 2, question 5. I read, the question that the position vectors of the points A, B, and C are A, B, and C respectively, where A is 3i plus 6a, the position vector of B is 5i plus 3k, and the position vector of C is I plus k. Find A, the vector product AC and AB. B, the vector equation of the plane ABC. Now, as a solution, A says we should find the vector product AC cross AB. Before we do this, we need to first of all find the vector AC and also find the vector AB. Now, the vector AC will be given by the position vector of C minus the position vector of A, which is I plus K minus 3I plus 6K. This simplifies to negative 2I minus 5K. Next, to find the vector AB, we have the position vector of B minus the position vector of A. And looking at the position vector of B, we see that it is 5J plus 3K, while the position vector of A is 3I plus 6K. So the component of I in the position vector of B is 0, which means that 0 minus 3 gives negative 3. 5J minus 0, because the component of J in this one is 0, gives 5J. Plus 3K minus 6K gives negative 3K. So, with the vectors AC and AB, we can now cross the product AC and AB. And to do that, recall from your work in class that the cross product will be given as follows: IJK, the determinant of this, -2, 0, -5, -3, 5, -3. And to find this determinant, we cross the I column to have the determinant of 0, -5, 5, -3, minus. Crossing the J component is always negative. So we take minus the determinant of, you cross at the J column, and you take the determinant of the matrix -2, -5, -3, -3, plus crossing at the K column, we have the determinant of the matrix -2, 0, -3, 5. So this simplifies to 0 minus -5, which is 25, 6 minus 15, which is -9, and this negative makes negative minus, or minus -9J, plus -10 minus -0, which is -10K, giving us 25I plus 9J minus 10K. Thus, the cross product of AC and BA and AB is 25I plus 9J minus 10K. B part of that question says we should find the vector equation of the plane ABC. And please, you must first of all ask yourself, what do you need in order to find an equation of the plane? You bring out the form of that equation. You will need the equation in the form R dot N equals V. Okay, now, how do we find the vector N? The vector N is always AB cross AC. But since the cross product is not commutative, AB cross AC is equal to negative AC cross AB. Please note this relationship, very important. AB cross AC is equal to negative AC cross AB. Now, AB cross AC is the normal vector as we have indicated. That is, the normal vector N will be equal to -25I minus 9J plus 10K, as you can see here. The position vector of a point on the plane is A, which is 3I plus 6K. With this N and A, and expressing or using this form R dot N equals Z, where Z is equal to A dot N, we can find that Z, or simplifying that Z, we have 3I plus 6K dot -25I minus 9J plus 10K. And again, multiplying corresponding components and simplifying, we have -75 plus 0 plus 60, which gives -15. So the quantity D is -15. And therefore, the vector equation will be given by R dot N, which is R dot -25I minus 9J plus 10K equals -15. So this is where we end with the application exercises. But before we go from this lesson, or before we end the learning session, let us take home some exercise of practice. So get a pen and a paper, write down this exercise of practice, which is also part of GCE 2007, paper 2, question 4. That's where it has been taken. And try to also solve to practice what has been explained. And please, if there are any difficulties, you leave a comment in the comment section. If you have not yet been part of our channel, please don't forget to click on the subscribe button and the notification as well, so that subsequent lessons will always get you informed. Thanks for listening, and see you next time in our next lesson.